So, good morning, dear participants. Today is the third day of the 1 week Atal FDP sponsored by AICT. So, today's chief guest is Dr. Dukka Ravindra sir. He is from NIT Allahabad. So, let us have a brief biography introduction of the today's chief guest. So, Dr. Dukka Ravindra sir, Assistant Professor, Electrical Engineering Department, NIT Allahabad. Sir did his PhD from IIT Roorkee, and Sir's area of expertise in applications and control of power electronics in automotive, transportation, and renewable energy systems. Sir has 4 patents and 16 journal papers, 5 book chapters, 19 international conference proceedings, and has 11 projects. Sar has guided 3 MTech students and acted as a keynote speaker in several conferences, workshops, and STTPs. Sar is also reviewer of the International Renewable Journals. Sar has received Best Doctoral Research Award in IIT Roorkee 2020. And Sar received Best Innovation Award from Zurich Energies Private Limited IKMC Innovation Award also. We are thankful for acceptance of the today's FDP session. So welcome you, sir. Thank you, sir.
Dear participants, the SAR has a good experience in power electronics devices and related projects. Try to interact with the SAR and try to get the knowledge and try to write the research papers. Okay, so thank you. Sir, just start the session, sir. Thank you.
Yeah, thank you very much, sir. Satish, sir. Devabu, sir, for making me part of this meeting. Thank you very much for the management of Vietnam Institute of Technology. And thank you very much, participants who are attending this session. Without further delay, let me start the session. Yeah, so very good morning. So now we are going to start our discussion on AI and machine learning techniques in microgrids. And also, we will see the things on the MATLAB, like hands-on, like how we can make a microgrid and how we can even apply these techniques from AI and ML techniques to the microgrids. And right now we are in facing lot of issues because of the most population growth. Like countries like India, we have a lot of population. Because of that, we need like to meet the energy needs. We need to go for the renewable energy. If you go to the renewable energy, there's a lot of renewable energy sources are there. So if you want to extract the power from these in distributed manner, then there's a need of this DC circuit, and also this DC circuit we can interface with the main grid if we are having any patches in the area. So how we can do that with the help of this ML and how we can make the models. We'll see with the help of MATLAB in this session. So and also this small micro is also there in case of electric vehicles, right? So in case of electrical vehicles also how can we make a small DC micro? We will see in the next slide. So you see that here, if you see that complete electric vehicle on that, we have this on the chassis, we have solar PV modules, and inside we have this battery pack. And also some electric vehicles what they're doing is that to extract to make that good dynamic when they're using some kind of supercapacitor. If you're having this kind of a sources, when you are making a DC bus, so it is also acting as a, like a small DC grid. So we'll see that even for the CE or real microgrid, how we can make the simulation model. Let me open that. The MATLAB. And what is our the scope of discussion? Is we can plan. Let me. Okay. So now we see that we have the solar PV source here, and then we have a supercapacitor, we have a battery. With the help of these three sources, we are trying to make a DC link over here. So this DC link, very like DC bus we are forming to meet the elements of the DC loads. Right. So how can we make a small DC network with solar and battery and so forth? Even we can interface with solar so with that in the next phase. And how can you manage when you're having a more number of sources? Right? How can you manage these things? Like how to manage the energy between these things? These sources which you are having in your DC in the at particular time to meet the load. Okay, so in that there are various this AI and ML techniques are used to energy management in this simulation. So how to make the simulation model we'll see like step by step, and then we'll discuss before that we'll discuss the theoretical background is required to make this diagram based simulation. Okay, step by step we'll do that. So and also the same responsibility we have in one of the project. I had an opportunity to make this complete responsibility. Here you can see that we have the supercapacitors here, and then we have this is like programmable power supply. This programmable power supply is acting like a battery. Right, so this we have programmed this programmable power supply with a battery characteristic so that it is acting like a battery. Right, so this is what the capacitors we have here. 10 kilowatt PQ minus programmable power supply. This is acting like a solar PV. This is acting solar PV generator. This is Japan line. This is Germany line, and these are crystals of capacitors. Right. So when we are having these three sources, right, we are trying to make a DC bus. And the DC bus we have a resistor. Even this DC bus with the help of that we have also tested EV also. Like the first objective is that this magnetic power DC bus we need to make, and with the help of that we are trying to run the loads as well as other type of loads like lamp or the resistor. Right? So that we will see step by step. In the next slide, you will see that we have this complete setup. Here you can see that this is a PMSM drive, and this PMSM motor to drive that we have this converter over here. This is the exchange load that DC bus. Right? These are various converters which have told here we have a battery and a programmable power supply and battery and then we have a PQ solar PV emulator and supercapacitors we have to extract the power from these sources to form a DC bus. We have the silicon carbide based converters. These are the silicon carbide based converters. Actually, conventionally we use a silicon. Silicon we have a converter which can offer very good performance. To drive them, there are a lot of challenges. How to address them, we will also see. Once we are done simulation, we see some practical aspects of the answers and to drive various loads, including electrical load, but we see that.
Sir, one doubt, sir. What is the voltage level of the DC bus,
So actually, in this practical setup, we make 240 volts. 240 volts. We have a PMSM of 240 maximum is that we have set it up 240 for this. This is the complete setup. Now, actually, when we make some kind of a converters, maybe for DC, maybe for any applications, actually, how the things are very based upon the driving factors. Right? Like based upon our DC microgrid has specific discussion on the DC microgrid. So, what is the main constraints we need to keep in mind when we are designing it. Like we have various requirements for the customers when you make some kind of a product. Like some customers want very good cost, like economical, this is your low cost, and some customers they ask very good efficiency, some customers they ask very good lifetime, some customers they ask compactness and weight. Right? But we, specifically in this decimated case, we need to focus on few aspects. Like one is that when you are making this decimated with the person and resources, so we need to keep high priority to efficiency and then the cost and then reliability and then compactness and weight. This is how we need to give a priorities to this decimated case. If you are if you are making a small decimated within electrical vehicle, as I said, that we have batteries in some cases there is in solar to extract some kind of power by placing some solar PV cells on the top of the chassis of the EV and then supercapacitor they use in the supercapacitor are very good dynamic performance coming to the batteries are very like they, although their energy density is very high, the power line peak power handling capability, peak power densities are low, that's why to handle very dynamic kind of loads, like if you want a very good acceleration, like in sports cars, in all the cases, we need to have a very good acceleration. But in that case, only battery powered source if you're having the EV it will not be able to provide you very good acceleration. So if you want that, then we are having supercapacitor. So battery, supercapacitor, and solar, typically these three, therefore these three are going to be receivers. So inside EV also, if you are having different sources, we can say that it's only single. In that case, we have changing our priorities. Priorities and the parameters. Priorities are compactness and weight, and then the cost, and then the reliability, and then the efficiency. Like that, we need to do. So this is like we have various architectures are there in case of DC microgrid when you are having more sources, like more energy storage elements. Right? Then the various architectures are there. They have been proposed in the literature. One is that we can see that basically these when you are having like let us take with the help of two energy storage elements I'm discussing, and here we are having more than two energy storage elements like battery, supercapacitor, and other type of batteries, I mean fuel cells also like when you are using electrolyzer, right? So to fuel cell they will generate the electricity and to get the hydrogen and oxygen, right? We need electrolyzer. For the electrolyzer, we need again electrical energy. So, like typically, we can say that in some cases we are using also fuel cells. Right? So, when we are having more number of sources, we have different architectures there. One is that passive power, one is that passive architecture, and second one is the active. We say that this is the allocation is there, so we say the passive power allocation architecture, and then we have active power allocation. Right? And then, like we have there, what we do is that we are having whatever sources we are having, like so, battery as a even I have included in the next slide the solar also. So first we will discuss with the battery and then we will include the solar, more sources. Right? So let us take when we are having two sources like battery and supercapacitor, we are forming a DC bus. Alright. So in that case, if you wanted to make a DC bus with therefore battery and supercapacitor, what you need to do is you need to have both the battery and supercapacitors have same voltage rating. Otherwise, parallel. And another thing is that they should have a typically almost like a same characteristics. You can connect them parallel. Otherwise, what will happen? Then any mismatch is there. There is some kind of a current maybe circuit between these two or compared to the supercapacitor. Sometimes they may dangerously harmful to the other source. So you need to take care when we are connecting battery and supercapacitors like in passive manner to the receivers. We need to take their characteristics are like more or less equal. Otherwise, we need to have some kind of a static or dynamic equalization. Circuits we need to employ. Right? Although they are also again passive. right? When you're making a static equation and dynamic equation circuits, right? Those and then also we have different ways to equalize the static dynamic characteristics. Right? So here we say that it is a passive changes means we are having only passive methods, right? So we need to take care about that. And second thing is that here we don't have a control on how much power you want to extract from the battery, or how much power you want to extract from the supercapacitor. It depending upon their internal impedances that will be decided. So you don't have a control. That is the main drawback here in case of a passive basis. But although it is very like it doesn't need any additional thing, so it is like economical compared to other methods which are going to discuss. We see that. And see that in another way is that in case of active, there is various architectures are there, like fully active, or semi-active, or multi-level. Multi-level means when there is a more number of sources. Alright. So here, in case of fully active means whatever sources you are having, all the sources they have a dedicated DC-DC converter, so that although their voltage rating is different, you can get your desired DC bus by controlling the DC-DC converter, so that you will get your desired voltage. Alright, so one thing is that here, let us take your DC bus is 48 volts, you need to have a battery of the 48 volts, you need a battery of supercapacitor of the 48 volts. But when you're coming here fully active, you doesn't have that kind of a constraints on the selection of the batteries with the voltage rating. You can select 22 or 24 or even like 10 or whatever. Even whatever voltage rated batteries you have, yes, you can get the desired by selecting a proper, designing a proper DC. You know, we have, let's say you have 24 volts or 25 or something. You want 48, so you can design some kind of a boost converter. It can give you like 22 to 48 or 24 to 48 or 26, whatever. There is no constraint on the selectivity of the batteries here. But here you need to have only one voltage rating batteries we need to select because you are tying battery with the directly with the receivers, right? So that is the that is another drawback of passive access. And this is a good point in case of fully active access. And also, we have a DC converter. Yes, you can control the DC converters with current control. Right? When you are applying a current control and you are fixing the output voltage, so you can get desired power. That is right. You have your load needs 10 kilowatt. Well, that's right. If you like a battery, let's say from battery you want to do 8 kilowatt and from solar watch you want to take 2 kilowatt. Yes, that kind of provision is there. Even if you want battery 3, 7 and from the solar capacitor 3, or vice versa. Whatever power you want from these sources, you can independently you can manually you can get it. But that is not possible in this facility. Right? These are the advantages. But the downside is that you need to have a dedicated DC converter for each source, so that will not come structurally to be into some kind of a cost. Alright. But in terms of a performance, this is good because we have a lot of options we are getting to get a regulated DC bus. Alright. So this bus is not so much well regulated because it based upon battery SOC state of charge. Already characteristics of a battery is decided by the SOC. SOC. So when it is like more than 80% or less than 40%. There is a steep changes in their resistance accordingly the current supply to battery or supercapacitor. We'll see even in the afternoon session we have something on the EMS. Then we'll see that how it is going to be affected. Okay, so what I wanted to say is that this is having very good in terms of the performance. Right? And only the downside is that you can have dedicated converters. Alright. So and yes. So another act is fully active. So what we are having, we are connecting all these DC converter each source which we are having. We are connecting all of them in a parallel. That's why we say that it is a parallel fully active. Similarly, we have another architecture called cascaded fully active. Here we are connecting battery and DC converter and then super the burner and these are connected in cascaded manner. Alright, so what you need to do here, so you let us take if you're connecting like this, you wanted to have some let us take 10 kilowatt power here, that and that this is although it is like independent control is possible and independently how much current you wanted from each source you can get it and how much power you wanted from independently you can get it. But the problem here is let us take this battery from the battery you are taking it and from the solar capacity you are taking 7, let us take 3 and 7 drop is 10 I wanted. Right? This, yes, this DC converter should be sized for 3 since you want it from battery is only. But this, although this supercapacitor is only contributing 7, but this battery power also should come through this part. So that's why whatever you are designing here, that should be of also 10 kilowatt. That is the problem in case of cascaded fully activated. Right? But another advantage is that since your battery, the voltage can be very low compared to this case, right? Because your battery, let us take your battery voltage is let us take 4 volts. You are stepping up, let us take your supercapacitor voltage like 20, right? 5 times you are stepping up, or let us take your 4 and your 18 and then 18 you are making it 40. So this voltage here it is very low, even with the conventional like that. That is an advantage, but the downside is that these converters, in one case which is near to the DC port, that should be sized for higher power rating compared to this case. That is the downside of this. That's why more among all the things which we have so far, this is the best one. Similarly, we have another architecture called semi. Right. What is semi-active is that this is like a mixed version of this passive and active. In case of the semi-active, we can see that only one of the converter, one of the sources is having a dedicated. Alright, like it is like a mixed, and there is a fully active converter. In case of semi, there is no. In case of in case of a passive, there is no any converter, but in case of semi, of the sources having a dedicated. Alright, means it is like mixed version. Here, let us take if you want to discuss about this, it is like we say that supercapacitor matrix. Why we say that supercapacitor only, although they are because supercapacitor is unique. That's why we give a name that supercapacitor semi-active. In this architecture, it is like battery semi-active. Why? Because battery having a whichever source is having DC converter that can have an independent control, alright, of the current and the power, you can get regulated DC process that possible until like mixed variant of this passive and right. And when you are having a more number of energies or like storage elements or sources, then some are connected to passive, some are connected to non-DC. If you are all are connected to the DC, we say that it is like multi-level activations. And some are no sources connected. Although you are having a more number of sources. None of the sources connected to DC. Then we say that it is multi-level passive. Like some sources are connected to DC, some are not connected. DC, then we say that it is a multi-level, some are active. Like that, there is various architectures. We'll take that as I said that in previous case we have discussed battery and solar. Now we are trying to incorporate solar. Okay. And among all the architectures which we have discussed, I said that this is the best in terms of performance. Right? So that we have taken here, and that this is the architecture we have seen in the previous slide. Now what we done? We have make a solver. Like it is like a DC, small DC microgrid. Right? Uh, right? So we can have various kind of DC loads we can feed. Alright, so this is like so that there is some kind of typical. This is like a pulse load. Pulse load is very critical for which will give a lot of stresses on the sources as well as the converter. So that's why if you can able to sustain or converter is able to give such kind of loads effectively, if they can heat, the power to sustain the load. That is the best case. That's why I'm taking worst case scenario. And this is the simulation. This complete system is shown in the mathematical. Now we'll discuss that. Before that, we need. Let us say you want to apply say techniques or machine learning techniques. This microgrid. We need to have a deep understanding about the system, mathematics. First, theoretically, if you want to develop anything, first you should have a very good theoretical understanding of the system. The second thing is the mathematical understanding of the system should be clear, and then simulation, and then experimentation. There are the four stages which we should have a very good sound knowledge. Right? So step by step, we go through it. Right? First, we go theoretical discussions, and then in the today's session. Alright, so now first we'll discuss with conventional and then we'll discuss with the to manage the energy in case of a DC. Alright, yes. Now, alright, so now first I will give you the basic idea how we are going to manage the energy between these two. Alright. So, what is the key idea is that the main idea is here. Let us say we have the load is like you have pulse load which is like varying load. Varying, right? Let us say a particular operating point, let us say you want it empty. Right. So you battery, a supercapacitor, or solar have a three sources. Now this 10 kilowatt can be achieved from only one source or two sources or three sources also. Or if it is a two, which are which two? Or if it is only one, which one? Right. We need to select in a best possible way. In that case, your overall system performance or utilization will be improved. Right? So that is the here we need to manage the powers or energies of the various sources. We need to have a smart way to extract the power from the various sources. Yes, we need to see. And in that power allocation schemes, I will show you the literature also. We have a lot of researchers done a lot of research and by using this and fuzzy neural methods or adaptive neurology techniques to allocate the power more and more effectively to extract the power from various sources in this DC method. So as I kept it, a lot of references are there which are exclusively on this power allocation. Will come to that in the later stage. How we can make what kind of results they have done. Literature review on uh, this power allocation and also the control. The control also using this AI and right? So first we'll talk on the control side and then we'll go for power allocation. Alright. Before that, we have various applications. Also, directly I am starting with this in case of a DC method. Like that, AI and ML having a lot of applications. We'll discuss them once we have some idea on the particular point. Otherwise, if you want, we can discuss now the AI and ML applications in power systems are DC methods. Equally, so these AM ML techniques.
Vlits, increase the brightness.
Okay.
Okay, yes, sir.
Okay. So now, like this AI and ML having various applications, power systems, or DC. Alright, so we can use this for maintenance purpose, or control purpose, or design purpose, or forecast, or cyber security. Nowadays, we are also hearing a lot about cyber physical power systems. Right? So, there are various cases we are having applications. In this session, I will show you this build connected case and standalone case, or we can apply this AI and ML techniques in the math. Although it is having various other applications, right? So we have a limited time, so with that we'll focus the MATLAB how we can make the simulation model using this array and ML techniques. Alright, so applications having like used in various areas, so optimization, effectiveness, classification, regression, like in design and forecasting, control, and maintenance. So we have a lot of, like in the literature you can see that a lot of applications are there with help of AI to the microgrid, renewable energy systems, in areas of design, forecasting. And while you are designing, let us take agricultural examples also. Let us take you are making some kind of solar PV system. You want to make a complete design of solar based some grid control system. Your physical system is something, your PV module is something which you are having physically, and the same thing you wanted to design a model in your system. Right? We are making electrical equivalent circuit. When you are making electrical equivalent circuit, there are various electrical equivalent circuits. Designs have been provided by the designers, researchers, developers, and various parameters we need to know it, add the design parameters by using this AI. That forecasting, like we are having a lot of data of the past data we will collect it, and we based upon the past data we can forecast the load demand of power generation. Right, that kind of application is also very using AI, so that you can effectively utilize the resources. And also control. And here, with my background is more into power electronics, so in power electronics, we see that the basic definition of power electronics are like conversion, inversion, and control of electrical power by using the solid mechanical rest. We say that is the power. Like control is an integral part of a power electronic system. Right? So when you wanted to make some kind of a power, control is must. So we can use these AML techniques to control our power demand, to get our desired performance. So for maintenance purpose also we are using this AML. Like in case of a microgrid, let's add that how we can use various things in case of design, forecast, control, maintenance. Anyway, we'll discuss the examples. As I said that parameters when we are designing the solar, like in the case of even solar PV, when we do the modeling, there is equivalent circuits, like single layered model of PV, a double layered model of PV, a three layered model of PV. What exactly is that? So, like here we are getting a VPV and IPV based upon certain temperatures and radiation. But that, like this temperature radiation keep on changing, then your voltage and current also will be changing. But because in case of a solar, for PV current is, if you see the equation, it is nothing but ISC G by G, not in 1 plus alpha delta T minus VPV by RS, VPV minus IPV into RS by RSH minus so that is nothing but your IPV. If you see that the IPV is a function of your temperature and area G and T, which I mentioned in that equation. G and G is nothing but the radiation, T is nothing but temperature. When these two are changing, you are getting VP and IPV varying. When these two are varying, like in real time, this is keep on varying, and then in your simulation model, you need to, like in the data sheet, if you buying some kind of a PV modules, they will not give you these RSH and RS and air quality factor, whereas like in some markets they are giving RS, like in last year. But only few data they will give and they will not give some other parameters. So you need to extract that to make, even although you are making this influence circuit, your real-time data physical model, whatever it is giving at the particular temperature reduction, whatever voltage and current is coming, and this IP and VPP, they are not correlating that much accurately. That's why that is what they have found, and then they have developed double layer model. And if you want to use this further, then they are making this model is more accurately giving than this service. Right? So that is how the researchers are working on this parametric identification. Right? Various parameters you need to know while you are making equivalent circuit in case of a MATLAB model, right? In that case, like mathematical model or MATLAB model. And in that case, you need to know various parameters. In this process, by using this, one of the applications I have taken like adaptive interface. Alright. Through this, they are finding out various parameters, like I said, the RSS, the right quality effect, they are keeping three right. And it shows that this application also in the matter. How can you extract the performance parameters? Like I said that we have taken, this is the module I have taken JKM 360 M72. This is German make, German building modules, for which they I will show you the data sheet. I kept it in the PPT. And now that, if you see that, let me show you now. Let me see. Alright, so you see that this is how typical feature said right now. This is the data sheet of this 3D model. Right? So this will give you 360 watts. This is the model which I am referring. JKM 360 and 72. Right? And this you can notice that they are giving maximum power 360 watt, and then maximum power voltage EMP 39.5 or IMP 9.1 open circuit voltage module efficiency at standard test conditions, optimal temperature, maximum system voltage, maximum series fuse rating. And you can see that they are not given any RSH C or the quality effect. Like until you don't get you don't have that parameters, you cannot make the equivalent circuit of this PV module inside your map. Right. So that's why we need to go for this parametric identification. That's what I wanted to say. This is one application where we are using this AML. Alright, so how we can do that in the MATLAB with this parametric identification, I will show you. So we can identify whatever just I made a MATLAB model. Just you feed this data and it will give you, just run that code and it will give you whatever parameters you want for that circuit. Right? So that the data can utilize in the MATLAB to develop model. Right? Like that, we are using this AML. Right? So, various even intelligent methods also they have applied to identify the parameters. Right? So various like technical algorithm in some of the reference used and particle format formulation, artificial immune system, artificial equality method, pattern search method, like this. Using this AML to find out the parameters of double layer model or single layer like that. We have used by using different methods to find out the performance parameters. So like that we have. And also like forecasting, like in the forecasting also, the trading will be in billing. Alright. We need like to have you can forecast the things perfectly so that you can accordingly if you forecast the things perfectly then you can that need, so that they will not be wasted. So in that process also, some people they are working on applying this in ML techniques in the market. Right? So that application also there. So like in PC we have this kind of and also like now in US we have this NRE, right? National Renewable Energy Laboratory. In US, what they do is they are like they have like a huge data based upon the city, based upon the locations. Right? Even in the Google, you can find that. Like, let's take in Java, what is the weather conditions, and like they are forecasting, right? Like after 2 days or after 3 days. Uh, like in even in 2016 when I was in US, like if you like the data of US, they have very accurate. Even after 14 days, at so and so time, what will be the weather? They are accurately forecast because they have accurately have a past data. They have collected various locations based upon the past data, and they're applying the same and to break the things for next 14 days, something like that. But not like in India also now we have ISRO and they are also collecting. We have dedicated satellites to collect the weather data, and once we are having stored the data, and then by using this ANML, we can forecast some weather conditions or something like that. So once we know the weather condition, that is like so and so time in next 2 days or next third day. So what will be the temperature elevation so and so time? If you know that elevation and temperature, then you can plan the things. You can effectively utilize your PV, and then the PV is a part of your power system or mental grid. Then you can plan other power extractions from other sources so effectively, right? So, and also we are using this ANML, right? Like as I told, like since this NRL having very good data, past data in US, and they also have some data in India. At particular location they have used data sets, and not all the locations they have because they that is not their scope, right? Because now we have in India, we have also dedicated satellite plants by ISRO. They are collecting, and once we are having a huge perfect data, then you can predict the things, temperature, whatever, right? Humidity or whatever, the thing, other things you can predict perfectly, and you can plan for power generation so effectively based upon the load forecasting also, right? So in that case, we are using this, right? So alright, that's what I said. And this artificial intelligence applications also there in case of grid connected PV systems, right? Not only PV or any other grid connected case, right? We can use these techniques in case of control. Let's say we are using a fuzzy control and this. Right? We will see that in with some block diagram. From that we can understand. Even in the MATLAB, I will show you some examples how we can apply the same techniques. And the problem is with this when you are using fuzzy or annex or something like that, your process should be of very good quality because you have let's take at the end your all the whatever system you are building in the MATLAB. MATLAB at the end is a digital processor. Right? All the things are executed in okay. So when they are like you are having more number of rulers that you are using applying your fuzzy control. Right? There is a lot of rule based unity create. That rule based unity create based on the number sequence based upon all these things. Your controller a lot of burden on the processor. Although, like we say that this fuzzy control washing this is or something like that. When we are implementing that fuzzy or AMPIS on the real time, there is a lot of we need to have very dedicated fast processing processors must be there. Even you see that your general purpose processor very high cost. That is like we are using in case of in your PC. we are using a processor like 64-bit, let us say we are using 64 system, 64-bit processor. With that, we have a latest variant of the processor, like i7 or whatever. Even then, if you are making a small, let's say I will show you some example, fantasy, that first we start with the book. Even it takes huge time because like you are getting a lot of number functions, how they will be executed at the end, we will see. Right. That is what I wanted to say is that when we are implementing these kind of air-based control to the real systems, we have a very dedicated, sophisticated processors to be there. Then only we will be implemented. Although we say that fuzzy washing machine, they are not really fuzzy. What they do is that they are, when we are controlling that motor inside that washing machine, right, we need to have a control. The control parameters have been tuned and that the modes, all these things will be selected. That will anyway, we will see in our case how we can employ that. Right, so there like the complete block diagram of that. Similarly, we can use it for monitoring, condition monitoring, like we collect the data of the battery of your PV cell or supercapacitor. Various points you can collect the data. Right. You can see based upon that data whether the system what is the state of that particular component. You can see their condition whether they are healthy or they are at fault. You can predict it because you have this model ANML. You have trained that. Let us say we are using your so in that case, you have part like you have LT system, how the data, you have fault data, how the system, even in the fault case, various kind of faults of the data. So once you are having your system, uh, your neural network system is fine, then the live data which you are getting from the your components, right? Based upon that, your system can see your system can tell that this PV is in healthy condition or fault condition, it is a fault condition or fault, all these things can be done. Or we can call this machine learning various skills we can apply. Right? So control mechanism monitoring also we can utilize this and so as what I said, like it can take the data and collection, then we can utilize like what kind of fault it can tell, and accordingly it will tell the fault, okay, this is the fault, and we can use that data to diagnose this. Right? So that is what I want. And also reliability analysis of the power control area of the right. So, alright, so like in reliable, I mean, let us say, uh, you have a lot of power components, let's say in power device. Power device is made up of like various kind of semiconductors, maybe MOSFETs or IGBTs or diodes or like that. And best like these devices, they are very sensitive to the temperature, operating temperature. Right. So these operating temperature getting affected by the losses. Right. So if losses are increasing, then temperature will increase, and temperature will keep on increasing, and then it will damper the device. So, like based upon these profiles of the losses or something like that, you can say you can utilize these techniques to tell, see the thermal profiles, and then you can safely operate the things uh, if you know the profiles. Anyway, and also nowadays we are making a digital twins for particular system. Like if you have some kind of system, you can make its digital twin. Right. So in that case also we are using this techniques to make our physical model which we are having, and the exact replica you are making in our display, and you are also using the cloud, and you see their performance. Right? So in this purpose also we are using this. And also nowadays we say that a lot of cyber physical power systems when you make these digital things. And we are keeping it on the cloud, and from the cloud we are controlling some of the things. In that case, what we some people when they are making some kind of they are doing some kind of cyber attacks. There are various kind of cyber attacks like DOS, denial of service, or FDI, false data injection. Right? So when we are having that, right? When there is some kind of cyber attack is there, and then whatever the data you are getting, the data is correct data or cyber attack. Right? If it is cyber attack, what kind of cyber attack? So these all can be predicted with the help of this physical process. Alright, so you get a cyber attack, have the various kind of faults, and then we have to detect these kind of attack. Accordingly, you need to do the cyber attack mitigation. Right? If you can identify which kind of cyber attack, and accordingly you can do some kind of mitigation, then you can bring the system to the normal state. In this case, also so there are various ways we are utilizing this nano. And so now we see for one application of my cricket, now we are focusing here. Right, so now I'm here and we discuss here. Now we are seeing some of the applications of the nano and we can start this general process. Alright, so you see here what I wanted to say. In this case, we are using this AI techniques to manage the analytics effectively and also control this converters. Right? We can use this AI techniques. That is one of the applications we are discussing one here. And also another application is that when you are making this model, right, we are using this to parametric identification of the solar PV and also batteries. Although like you have a battery model or PV model inside your MATLAB, they are not like accurate enough or super capacitor. They are good, but they are not like 100%. They have a lot of limitations when they are modeling. The MATLAB also someone has model. Right? So we can make improve the model. When you are doing that, if you are making a whole model, then our concepts will be improved, how they are model the battery. Right? When we say that battery is taking a constant DC source, but it is not actually, right? So even 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 when we do the model, the battery as a particular PV, there are various methods are there. Right? We need to investigate them, which one is good, we need to take the best one, right? We will see that in the application also. Right, then only you can make, if you have a good model of your solar PV, good model of battery, good model of your supercapacitor, then you can design the converters perfectly sources. And then you can control them properly to get the right things to perform. Alright, so in that case, we are applying the same ML in this microorganism. When you see them in the slides and right? There is one application here. The second application is that here, what I said, let us say you have a 10 kilowatt load. The 10 kilowatt load can be expected from a single source or two sources or three sources. If it is single source, we have three possibilities. It can Together, two sources we have different solar, so PV and PV and which combination? And another case is that three sources. If it is three sources, you can take it from one from solar, then 9 is to come from these two, and then there is a lot of combinations are there. Which combination is better? How do you decide? So that you need to that you need to use the intelligence here to extract the sources. So the main priority here is to see the physics system properties. You see that we need to give high priority to the software monitors. If you don't extract the available power from the PV, that power is getting wasted. So you must extract the maximum power, whatever it is. Let's say I have based upon the remaining fraction of union, variance. Now, this P battery plus P supercapacitor should be equal to P load minus P PV, right? So once you know that P battery plus P supercapacitor, now again go to the physics. We know that energy density is very much battery and power density is poor. And you are going to use capacity. Whereas in supercapacitor, power density is very good. Uh, we know that the properties of these elements, then we are utilizing that to accept the power. What we do is, we now we know that how much power we want to get it from these two sources, right? And in that we decompose that power into two components. One is the high frequency component of power. Second one is the low frequency component of power. That high frequency component of power, once we decompose, how will we decompose? We will see that in the next. Once we know that high frequency component of the power component, that power component is acting as a reference to the source. And the low frequency component of power is acting as a reference to the power. Right? And then we know that power references to the battery and supercapacitor. And you know the voltage and current of the battery and supercapacitor respectively. Once you know the power and you know the voltages, then you will be able to find out the current. The currents and actual currents and reference currents you will take and you will be able to some kind of a control. Right? So the controller will control what is the duty cycles, right, to get the powers from the respective sources. That is how we will control. Right? So, we'll see. Then as well we'll see. Now, earlier we have seen with the two sources, now I included the three sources like a micro. The same like we have in the electric church, passive, then we have one. These are the complete architectures which we are having here. Right. And in this case, we will see how we can improve the performance. Alright. As I told you, I wanted to just tell you some improvements which we can do in the physical systems, and then we will go for the modeling and the control of that. One thing is that you can use this wherever system, whatever multiplicator you are making with this converters. In the converters, you try to adapt the wideband interface. In adapt the wideband interface, so you will get a better performance. That is what I said earlier. On the point we have discussed, the silicon carbide. Like if we are running a silicon, because we want a reliable operation and good performances. In that case, these vitamin devices cannot be very good performance. You can see the physical properties. These are physical properties like electric field and then energy gap and atomic velocity, melting point, and thermal conductivity. And I compare these three for these silicon. You can see that silicon carbide is better compared to the silicon. Silicon is like yellow, and you see that this blue one is very good for the electric is very high. So what does it mean? In the small size of a wafer, this semiconductors, you can blow a higher voltage. And energy gap is very good. And the electron velocity is high. That means that you will get a very high switching frequency. And you get a losses or leakage current is very low. And you can easily get good efficiency. Onstate resistance is very low. And thermal conductivity is good because of that you can operate at higher and higher junction temperatures. The junction temperature rise, case temperature and sink aging temperature. You can operate your devices so safely than your right? Because of that you will get when you are making an integrated with this kind of device, you will get a very good compact size microwave. Right? Why? Because of the junction temperature, your cooling system requirements will be low. Because cooling system requirements, so that you see heat sinks or something cooling and they also a lot of space. But also their weight is high. Because of that, uh, when you are adopting this pattern production of microwave, then it doesn't need that much big size casings and liquid cooling arrangements. Because of one of the properties that it is having good thermal conductivity. And another thing is that it's having a very low constant losses. Losses are low, like both switching and your conduction. Because your RDS is also very low, and also your resting dynamic times also very low. So, means that this requirement is low. So, when you make your converters with this kind of level, then your converter size might be low. And then your DC maker will become very high. Another side is that you can operate ISP when you are able to operate ISP. Let us take your making a DC converter. Their inductor and capacitors are required, right? So when you want to make in that case, what happens is that inductor and the capacitor are transformed. Funny, like uh, mostly will take inductor, capacitor in case some isolated amount will take a frequency. Right. So their size weight value is essentially decided by the frequency. Right? Let us take a simple conductive reactor. Let's say this is how much high you can go in case of the frequency, that much low you are. We increase the frequency by 10 times, the inductor value goes and then down. Because frequency is 100 times higher, then your inductor value goes 100 times lower. Right? Like that, like same thing with the capacitor, same thing with the means the smaller filters, the smaller plastic components that are there in case of the and also I wanted to tell you one thing. When you are making your microgrid and with these kind of advanced stuff, uh, they are giving you very good advantages which I was in the previous slide. And also their control should be so much sophisticated. You need to make a very good control. Otherwise, what happens is that there is a lot of stresses will be there. And even I will show you. Even you are connecting a two devices, two MOSFETs or one inductor and one device, your device, MOSFET and diode. Including a small wires is having a some kind of an inductance. Let us say even we don't consider in your mathematical model or in your simulation, right? But physically, if you take some kind of a wire, even I take this wire is having some kind of a conductance. Even it may be nano Henry, right? Uh, even it is very low nano. So with that will be like nano is like 1 nano is 1 into 10 power minus 9. We may ignore theoretical calculus. But in the system in which physicality is there, right? So when your devices are operating higher switching frequencies, even the small electrons create a lot of uh, effect on the system. I will show you that. Because when you know the effect, then only you can make your system perfectly so that you can control the things. Means at the end, you are using this AI and ML techniques to control in case of our system, right? So you need to control the devices so effectively. Otherwise, it will create a lot of stresses and then it will kill your devices. When it is, your devices are killed, then your means your MOSFET or IGBT are killed. Then your converter will not be able to give the satisfactory operation and then you will not get your decimal operation. Alright? So you see that I want to show you that. You see that on this slide you can easily understand. Like this is simple. I have taken a 600 volts and 120 ampere. These are hardware results actually. We have taken 600 volt DC and 120 volts low, 120 ampere low. Alright. This is like left hand side is this is the case in case of 600 volts and 30 ampere. This is in case of 600 and 120 ampere. During turn on and turn off, you see that this is the x-axis in terms of a 10 power minus 9, sorry, minus 7. Means, you see that it is like 1 into 10 power minus 7 means 0.1 microsecond. Alright, so it is very, in that span we are checking how the voltage and current. We need to have to check that we need to have sophisticated DSOs with a high bandwidth. Right. Like at least we have used the DSP of 1 gigahertz bandwidth, and you can get good resolution. Otherwise, your measurement is something else, and your real time stuff is something else. Alright. So see that I just given a 600 volt. It is simply a device and DC source and the load. Okay. So if you are giving 600 volt source, your device will experience only 600 volts. But it is not happening. You see that. Let us say during turn up you can see the voltage. If my source is like 600 volts, ideally it should be 600. But this is the effect because of our connecting wire is like between your device and your source. The connecting wire is having a inductance of 50 nanometer. It is creating huge stress. It will going even 900. That makes your device. Your device is rated for 600 volts. We think that your source is 600, your device is also experiencing 600, so device will be safe. But it is not. Because your devices are operating high switching frequencies. When they are operating high switching frequencies, then what will happen? This dB by dt and dA by dt also comes into the picture. We know that dA by dt or dB by dt, they are critical in case of a device, they may kill the device. Right? So this is like you see that dB is like 0 to 900 and dt is like 0.5 into 0.5 into 0.05 into 10 power minus 6. So that is a very when deep that is like denominator. Denominator is 0.05 into 10 power minus 6. If you go up, it's like 200 into 10 power 6 into this much 900. It's a very huge. Really, that may be the order. So we need to wisely. Anyway, I'm not discussing this. Okay, we'll discuss at the last once we got the assimilation and we'll see that. Alright, what I wanted to say is that when you are wanted to control your power plant devices, you need to have better understanding about the devices and the converter, and then you can apply better control. Otherwise, even though you are designing a good controller, devices may not functioning as per the requirements. so it may be also diagnosed. And when you are making a this microgrids, like we are using batteries and supercapacitors, solar anyway we are taking. Why we are to go for the supercapacitor? Can't we take different types of batteries and fuel cells and things like that? Generally, when if you include supercapacitors, the advantage is that it can handle that like dynamic loads so effectively. When there is some kind of a dynamic loads, all right. So we have dynamic load like if you want it instantaneously, we wanted to go for 0 to 10 amps within no time. That kind of loads cannot be satisfied by the battery, right? But converter is having also some kind of a tank to come to the steady state. Alright, so battery already is having some kind of a high uh, time to reach its final. Right, so if you are only depending upon EV and batteries, your dynamic loads may not be able to, their requirement may not be fulfilled. So that's why what we wanted to do is that we wanted to make your microgrid with the help of in that microgrid we are also trying to incorporate the supercapacitor so that it can handle all kind of loads. Right? These are the advantages of the supercapacitors, right? Like fast charging ability, high capacitance, very like compared to batteries, these are all advantages in this. Right? You see that, and also not only if you are taking supercapacitor, not only they are getting that benefits which I mentioned. It's also giving you good benefits in terms of cost and all these things. I will show you. Here, like this, we say that it is a diagram plot from which you can understand the specific energy density and specific power density plot. Like batteries have a very good energy density, and capacitors are also capacitors have a very good specific power capacity. From this plot, you can understand why we have to go for both the. And you see that, and from this, also we have compared when you are making a DC microgrid. If you include this hybridized nature sources, we are also getting overall. We are there is weight reduction of 15.59 and the cost reduction of 15.53 percentage. When if you are taking only batteries and to meet the energy demand, or battery plus supercapacitors, in case of battery plus supercapacitors, we are getting this much benefit both weight and cost. So that's why our microgrid is composed of supercapacitors. That's how we justify what are the sources we have taken to make our DC. Right? So we'll see that then modeling of this microgrid, and then once we understand mathematical modeling, then we'll go to the control. Right? So, where is this? So before modeling, we take break for we'll take break and then we'll start this modeling.
So, dear participants, so let us take a 10 minutes tea break. So, we will meet after 10 minutes. Thank you. And any participants that are having accommodation problems, so please contact me. Only evening, evening, sir.
Morning. Actually, morning 7. Not ఇక్కడ బీహార్ అస్సాం ఉంది వెస్ట్ బెంగాల్ యాక్చువల్లీ పెడుతున్నారు సార్ ఉందా సార్ పెట్టారు ఓకే సార్ కాకపోతే ఫారం లాంటివి చేసింది నా దగ్గర ఫైనల్ అప్లై చేసింది 2 పేజెస్ అప్లై చేసింది 2 పేజెస్ అప్లై చేసి ఒకసారి ఒక పేజ్లో 160 అప్లై చేసింది ఒక పేజ్లో సో 360 అంటే మన దగ్గర నుండి మన దగ్గర వస్తాయి అది ఏదున్నా సరే ఎంట్రీ లెవెల్ స్టార్టింగ్ లెవెల్ ఎక్స్పీరియన్స్ PhD అయిపోయి 5-6 years ఒక అతను ఇంజనీరింగ్ ఎంసెట్లో చేస్తున్నాను అతను వస్తుంది డూప్లికేట్ ల్యాబ్లో చేస్తున్నాను డూప్లికేట్ ర్యామ్ అని డూప్లికేట్ ఫస్ట్ ఐఐటీ ఎలక్ట్రానిక్స్లో పవర్ సిస్టమ్ తీసుకుంటాం ఎలక్ట్రికల్ లేదు ఎలక్ట్రికల్ స్పెషలైజేషన్ ఈసీలో కంట్రోల్ అలహాబాద్ నెక్స్ట్ నుంచి అది ఆఫ్టర్ మీరు ఉన్నప్పుడు చంద్రశేఖర్ ఉన్నప్పుడు దాంతో పాటు డైరెక్ట్గా కూడా అప్లై చేసుకోవచ్చు. మీకు తెలుసా ఫోటో స్టేజ్ లో ఫస్ట్ సుకుమార్ భాయ్ నేను అంబేద్కర్ పర్లేదు సార్ ఇంకా యాక్చువల్ అంత ఇన్ఫ్రాస్ట్రక్చర్ క్వార్టర్స్లో ఇంకా ఇప్పుడు కడుతున్నారు ప్రజెంట్ మన ఇష్టపడి మనకి ఇచ్చారు లేకపోతే బయట ఉండడానికి అది బాగా పాడలేదు యూనివర్సిటీ అందరూ వస్తారు అంటే మీకు అప్లికేషన్
బాగా కావాల్సి వస్తే
మీరు ఏదైనా దానికన్నా ముందు కూడా డైరెక్ట్ అప్లై చేసుకోవచ్చు మన ఈ రోజు ఎక్స్పీరియన్స్
లేదు సార్ డైరెక్ట్గా గైడ్ చేయాలంటే
అది కూడా అది చూడాలి లేదంటే
గైడ్షిప్ నాకు ఎలిజిబిలిటీ అది 2 years
అయిపోయింది
అలాగే 20 రోజులు అయిపోయింది
అప్లై చేసి వచ్చాను నాకు చేసుకుంటా ఒకసారి రిజిస్టర్ మన వాళ్ళ కొడుకు నా దగ్గర నష్టపట్లో అతను చెప్పాడు అంటే కొన్నాను
ఇక్కడ
లేదు లేదు నచ్చిన నాదే ఒక ద్వారా వాళ్ళ బెంగళూరులో అన్న చేయడం అంటే ఇక్కడ ఎంఐటీలో ఒక కూడా
Yeah, nice. Type of good.
అప్లై ఇలా పక్కన స్కీమ్ ఫండింగ్
Latest technology
ఒకసారి కమెంట్ చేస్తే నమ్మేసుకున్నారు ఇది ఇక్కడ మీరు అప్రూవ్ చేసినప్పుడు వస్తారా రావాలి ఇక్కడ ఇష్టం కాదు సార్ So welcome back, dear friends. So shall continue our discussion. So now you see that now what we are doing is that we are trying to model or design it so that once you understand the modeling, then you can apply our AI techniques to control our microgrid. Right? So how much better you can understand the mathematical modeling, that much better our controller will be. Right? So now we are trying to model our complete system. Alright, so we start our discussions. Uh, we see that first we'll start with passive, since we have various architectures as we have discussed a few weeks back. There we saw that running that passive based HESS micro. Here we have our DC bus that should be regulated. But if you want your DC bus to be regulated and at the same time need to extract the power to feed the loads, we are taking here a person load as I described earlier, a person load is a more critical load. Right. So to satisfy that kind of a load, now we are trying to model our system, right? Now you see that this is like first we take a first approximation of total battery based modeling, and then we try to improve our models for the battery and supercapacitor and then slow base, like step by step. For better easy understanding what is that first we can approximate capacitor model and the battery model, and then we improve their models accuracy. Right? How to do that we see. So we see here we have this passive this pressure. We are trying to convert this into frequency domain. As we know that there is a capacitor like 1 by C, initial capacitor, supercapacitor voltage VSC, and then we get VSC bias, resistor is like resistor in the domain, frequency domain. By that we are converted to domain to frequency domain, and we are trying to convert this into this Thevenin equivalent model. Alright, so now, while we are converting this frequency domain model into Thevenin's model, and we need to find out VTH and VTH. Once we are having VTH and VTH, our idea is we need to find out I bus. So our idea is that for a particular node, we need to make the DC bus is regulated, and for that load we need to get how much is contributed by the supercapacitor, how much is contributed by this battery, and we are finding out. So now we need to find out VTH. We know that when we are converting this frequency domain circuit to a model, we need to find out VTH and VTH, right? So VTH can be found out and ZTH can be found out. Anyway, stabilize the first capital here. See that these are Thevenin's model. I can just write a nodal equation here, then we get this, and then this is a node you can go to Thevenin's voltage. This node is having Thevenin's voltage, and this minus this V Thevenin minus VA by RIA is and the current here is nothing but this, right? V Thevenin minus VSCI voltage by S by this this RC, right? Combination we are keeping, then we get this current. These two currents will be equal to 0. Right? So to find out the Thevenin voltage. So then simplify further. This is I am simplifying. There are VTH I am making common and bringing other terms other side. Alright, so like this. Then simplify mathematically. Then this is what I got a Thevenin voltage. That is what I calculated. Right? This is what I calculated. How it came, I calculated step by step. This is how we calculate the Thevenin voltage for the passive arrangement. So and then we need to find out ZTH. Okay. How will you find out ZTH like that? ZTH is nothing but we need to deactivate the switches. And deactivated this one, these two are comes in parallel. That is what I reckon RLA is parallel with RLC plus 1 by S. Then simplify it. Very simple mathematical manipulations, mathematical simplifications, then I got ZTH. That is what I calculated. This is what I calculated. Once we got VTH and LTH, right? As I said, what I said that we are doing analysis for this DC bus in case of a passive based method. We are typical load is like pulse load. Pulse load is a very critical load. If you take a constant load, it is very easy for analysis, but we are looking at pulse load like on and off, and then how the system is behaving. Like it is, pulse load is having like both high frequency and low frequency component of current. That's why we have it. Okay. So now we can represent the pulse, you know that u of t minus kt. Here I have written pi, or we can take u or pi, whatever. Pi of t minus kt minus of pi of t minus of k plus dt. This is a like pulse representation. Then we are repeating the same pulse is equal to n minus 1. Right? That into magnitude. That is how we represent the pulse load current. That is what we have extracted from the DC pulse. Once we are having this, you can apply this Laplace transform on both the sides, then we will get I bus of s. I bus of t will become I bus of s, and u of t minus kt is nothing but e power minus kt by s. This will become this. Right? So we got the I bus of s. Once we got I bus of s and z thevenin of s already we calculated. We calculated z thevenin. V thevenin minus z thevenin into I bus will be the bus voltage. We see that here we have to see V bus in an what? What is V bus? V bus in an V thevenin minus I bus of s into Z thevenin. We have already now these three. So just substitute there, then we will get V bus of s. Right? So once we got a V bus of s, then we can find out that once we got this V bus of s, or one, then we can go for V bus of t. Once we know the V bus of t, we know VL of t. Between the difference between these two by RLA, then we will get a IAA of t. Similarly, we will get a IR. We know the I bus, we know IL, then I bus minus IL is nothing but ISC. So we are finding out all the components of this circuit, V bus of t, IL of t, IS of t. That is how we can find out how much current is run from a supercapacitor current is run from our band. So now we are doing this like there are a lot of mathematical calculations into the panel calculations. Alright, the voltage drop at Thevenin's, that is what I said, I was into the RTH and calculating it, that I am representing as a figure. So just we know what is the IOS surface is here, and that it is already we are done with that. Just put these two, then this is your that. Right. So that this I got it here and here. So this is your nothing but your region of S, nothing but IOS surface into getting of S. Now we need to do, we got V bus of S. Now I want actually V bus of T. Once we know V bus of S, now what we need to do? We need to find out V bus of. What you need to do? We need to do inverse Laplace transform. Just I am applying inverse Laplace transform to this Thevenin voltage minus Vz. Right? Because Vh of S minus Vz of S is that we do V bus of S. But we want V bus of T means whole Laplace. Right? So this Laplace inverse of this minus Laplace inverse of this. We do it, we'll do this and then we'll do independently and then we'll put it back, these two then we'll get a inverse. V Thevenin of T is the Laplace inverse of Thevenin's voltage. If you do it, VLA of S is nothing but VLA of T. This is as it is. And this will become more like e power minus T by tau. It is like 1 by R S plus, right? Nothing but e power minus T. That is what we have. So we got a VTH of T. Now Thevenin impedance, the drop we check. Now that we need to find out inverse. Doing a mathematical like a step by step, and we can see that this is like S plus A by S plus B into something like in S. So we need to do first separate the terms like this, and then simplify. Right, we do the mathematical process. For mathematical calculation, we need to do. Our idea is that we need to find out Laplace inverse of Vz. We do it, and finally we got that. Right? Uh, this is VZWP. Now what we need to do once we got we have find it out VZ and we find it out VTH of the data man. Now both I am substituting it, then this is VTH of this is a VZ of t. Put it back and we will get a V bus. This is how your bus voltage. See, bus voltage is not a constant. You see that it is like really is a constant. This is a battery voltage, but it is also having another frequency component. This is our interesting stuff which we need to know. Now it is not like constant DC, alright? It is having some other frequency components also there. When you are connecting a DC bus with a parallelly connected battery supercapacitor, that kind of voltage will be there. Alright, once you find it out now, V plus of t, now you can calculate our IL of t. I said VLA minus V plus of t by RB. Then you know VLA and you know V plus of t. Then just do simplification, then we get a IL of t. And then supercapacitor current is nothing but I bus minus IL of t. That we do. Then we will get both supercapacitor current and battery current. Right? Then this is a summary I kept it. See that from this whatever calculus I have done from so far. But all I kept it here. You see that bus voltage is if theoretically what we assume that battery voltage is very constant, so we get a constant voltage. But not, it is not constant. It is also has some other frequency component. We need to suppress this, we need to kill this, so that we will get a constant DC. Alright. So, like battery current is not like constant DC. It is also having some exponential term and some kind of some other exponential impulse kind of things are there. Similarly, supercapacitors also is not like non, it is also having some other frequency components. Right. Once you know this is instantaneous and you can find out the steady state components of battery supercapacitor. Alright. So, this is how we do some mathematical calculation for HCSS systems. Alright. So let me make a detailed report. Like what I told is that whatever I calculated this. Alright, so anyway, these are the things I calculated. But for others, similarly, at the final we got IL of t. It is not only DC component, also having something like that frequency. Alright, so this is what that is what like now I have taken some battery voltages and the internal resistance or physical battery we have, and then I calculated all the things with pneumatic example. Is the case which we made it. As I shown you earlier at the beginning, I shown you hardware setup for that, all the calculations. Now you see that this is like our various components of currents. We have calculated voltages and currents in both frequency domain and time domain. We have calculated. You see it. Like our V bus of t is not only having a DC component, it is also having 24.9 of DC component, but in addition to that, it is also having some kind of a frequency. We need to suppress this so that we will get a very good steady natured DC component. How we can do that? We will see that. How we will apply this AI techniques to suppress that? We will see that. Alright. So once we got the bus voltage expressions, right, for our case, and then calculate the currents, right? How much current is drawn from battery, how much currents are drawn from this. These are the step-by-step calculation. Each step I calculate. And once you, how much better, how much deep you understand mathematically, that much better you can correlate your simulation, and that much better you can make your control to that particular microgrid. Then you can apply, you can make your own better rules when you are applying this person or amps. Right? These are all essential. Like you know that property systems, like you need to make a knowledge-based rules, right? Rule-based you need to make. That is comes through the better experience and understanding, right? If you can make a good mathematical model, then your understanding on that particular system is will be so better, right? Based upon that, you can make a frame very good rules, right? Now, what I said in first case, in first version, we have taken a battery and so capacitor like very approximate. Now, what we done? Now, I am trying to incorporate. Now, you see that mathematical burden will increase. Of course, it will increase, but we should have a capability to solve that kind of a thing, so that you can make your currents or whatever calculation you make, that will be more and more appropriate. Now, I take a battery model. Earlier, we had taken only battery model. But there is not like exact match with your physical data and simulation. Now, that's why in the literature they have proposed a Morachan model, right? A battery modeling. That Morachan model is one of the popular techniques to model the battery. In that, what they have shown, battery is not only having internal resistance, it is also having two kind of branches. One branch called short-term branch, another branch called long-term branch. Short-term branch and long term. There is a two branches will be there. Each branch is like combination of R and S. The combination of these parameters, these counts, right, with our, again I said earlier, one of the applications is ML to find out the parametric identification of your battery supercapacitor. I will show you the supercapacitor modeling. First, before going to the hardware, at any time, any system, you should have a better, accurate model of your physical system in your MATLAB. That will come through proper equivalent circuits, proper the data, right? Proper. If you take a very good equivalent circuit proposal in the literature, you take that and you need to identify the proper parameters of that equivalent circuit. Right? That comes through this AMM. That I have already shown you the example earlier. One of the applications of AMM. Right? Through that, I have identified. How to identify? I will show you some scripts in the latter. Okay. So these are the values for the battery. Right, short-term branch parameter, short-term. This data, what we got from this MATLAB, this battery model I have taken, and I got the voltage and current data, and that is exactly replicating my real-time data. What a particular load and particular application, whatever you do, and different load conditions you extract, and then match both experimental and hardware, experimental and simulation. Then it is correlated. I will show you that. We have done all these things so thoroughly for both batteries, supercapacitor, and PV. Once you have a mathematical model, then we can complete estimate and then control. That's what I show you step by step. Now, if you increase the accurate model, then now complexity and the mathematical burden will increase, of course. Now we see that. Again, we have calculated. We need to find out how much current run by this VSC and ISC and IVAT, and then these two can be calculated once you know the V bus of T. V bus of T minus VBAT by this impedance will give you IVAT. Once you know IVAT, you know I bus minus IVAT is equal to super. That is how we are calculating it. So just proceed to follow. This is what I am displaying it. Now you see that in earlier case and this case the Thevenin's voltage, if you see it is like mathematically it is so expensive, right? So you can notice that earlier Thevenin's voltage is simple compared to this. And now in next stage we will go for inclusion of supercapacitor model is so better, and then converters we are including. We will see that. And then although mathematically sort of, but we are getting a huge understanding on what currents it is going, what kind of a voltage it is building. Once you know that, then we need to suppress that. Certain frequency components of currents that can be possible. Once you know that, what are the frequency components of it, what you want to suppress, then you can apply your control. See that. See that our V was up. Now once we have this kind of infrastructure, now we need to find out V Thevenin of S, then you need to find out V Thevenins of T. You need to do the inverse Laplace. Now it will become more tough. But we see that we have done it. And this is V Thevenin. Simplifying. This find Thevenins voltage. I got it. And then that I have taken inverse. Then you see that 57 equation is that my Thevenin voltage in T domain for this. Okay. So it is so extensive. You see that. Now you see that this is what actually Morachan model of the battery. That is what is that. This is what we have taken. Now what we are taking now we need to find out. Once we are having Thevenin's voltage in S domain, we need to find out Thevenin's impedance in S domain. That is what I am doing it. Earlier it was so easy, now it is becoming so tough. Thevenin's voltage also. Thevenin's impedance also. Mathematically you are following the same process. Once you are having some kind of circuit which can get some resistance capacitance, you do have to find out the Thevenin's impedance. That is what I did it. And finally we
All we have to do is manually.
yes sir, these are by hand mechanism. Alright, so we got Z Thevenin's of T in T domain. Alright, so once we got V TH of S and Z TH of S, then we can find out the drop across Thevenin's impedance. That is nothing but your we should know I was of S and then multiply with Z TH of S, then that is nothing but your VZ of S. That is what notation we have taken. That is what I am doing. I was of S for the same pulse load current, we know that I have represented earlier. The same load current we are having. Now just do that, we are finding out VZ of S. VZ of S is nothing but I was of S into Z TH of S. That is what I am doing. Once we are having VZFS, here I got VZFS. That I am taking inverse Laplace transform so that I will get a VZFS. That is what I am doing. And now, this is the generalized expressions we got it. Now, what we are doing is, we are doing it for specific case of our battery and solar capacitors. And now, battery and solar capacitors, yes, I'm putting it. Now you see that VZ of S and VZ of T, and then we are finding out once we are having VZ of T, now we are finding out V terminals of T, and then finally we got V bus of T. That is what our right? V bus of T. This is V bus of T. See that it's having different frequency components, right? We can notice that. So we wanted to suppress it because we want to skip DC bus. See that they have different frequency. We need to suppress. We will suppress. So this is a complete expression. This is a complete expression of our DC. Earlier you see that 28.4 or 24.8. This is the DC, and we have a lot of frequency components on a DC bus. Alright. Now it is like somewhat more and more realistic compared to the previous model which we have correlated. These mathematical models are validated with the power simulation model and practical data. Okay. Once we are having this V bus of T, see that we have a DC component 24.8 and but another frequency component. Now we are finding out what is the current from the battery, what is the current from solar capacitor. The process I told you, and the same process we follow out. And then you see that this is my ILF. This type of currents being drawn from my batteries. Okay, so you see that batteries also having not only DC currents, but also having different various frequency component of currents. Alright, so like this. Now what I did, we have seen the analysis for passive and then semi active and then active. You see that now the things have become more complicated now. Again, now you need to keep a DC converter. Yeah, yeah. Alright, so now it will become more and more tough because now DC converter things also will come into the picture. Let me show you. Is it like after that? If when you are going to the full HESS, the things will go more complicated. I will show you all the calculations now. We have done for all the cases. The same thing I kept it here. You see that in active HSS case, let me show you, see underscore. These are the calculations for active HSS. First, these are fully active HSS. Now we are considering all the things in the battery and then converter. Now follow the same process. Then this is the voltage gain by considering all the non-linearities of like all the parasitics. Then you see that follow the process which we have discussed earlier. Now, if you are calculating the stuff, now you see that there is a weight evidence, and now you see that it is becoming more difficult because it is like including unit ratios and your conversion gains and all these things. So you see that. The same steps which I have said earlier. First, you need to find out Thevenin's voltage, and then step 2 Thevenin's impedance, and then I was of T, and then step was I was suppressing VZ Thevenin, suppress VZFS, and VZFS, then we take inverse suppress, and VZFS. Same process which we have discussed earlier. But only now things are becoming more and more complicated because we are out of parameters we included here. So see that. Like this, we need to develop a complete mathematical model. Once we are having, then you can understand what kind of currents being drawn from battery and supercapacitor. And by selecting a proper filters, we can suppress those from the battery or supercapacitors. So that is the key idea. Until we don't know what kind of a currents are being drawn from the battery and what kind of that currents we wanted to eliminate from the battery. We wanted to shift that current from battery to PV or supercapacitors. Then the stress on the battery will be reduced and then the lifetime will increase. Or you wanted to suppress this from battery and you won't put it in super because supercapacitors have a high frequency component of current stresses. So they are good for that. So they are meant for that. So you just suppress from battery and extract the same because your load wants that. Right, because you are taking a critical load, pulse load. So load needs high frequency component of current also that you have to shift from battery to supercapacitor or to the PV. Typically this kind of current can be supplied from the supercapacitor. So extract from the supercapacitor. That is possible. First we need to know what kind of currents are being drawn from the battery, and you can bypass that component of current from battery to other so that overall things will be improved. Okay. Like this you can this is a like this you can do mathematical calculations for a complete system. Whatever I saw in the PDF I kept it. That is the mathematical calculation step by step I kept it there. And here is summary. Right. Alright. So once we know that these are the currents are being drawn from each case, then you can suppress, right? So now, so far, what we have done is that we have taken battery, and also if you want supercapacitor modeling, I will show you that. Uh, we have seen for uh, battery, right? So, okay, this is supercapacitor which we have used. Okay, so which I shown you earlier. This is the data sheet of that. So this is the we have taken this this is a common data sheet for different supercapacitors like 350 farad and 700 farad and 400 farad and 2000 farad. We have taken the slot from that. Right. So the physical and then this is the data sheet. This we have characterized. uh, supercapacitor data. So you event is in the slides and so you will enter. Okay. First we'll discuss solar PV. This is how the solar PV equivalent model, and then see that these characteristics of the real time from the data sheet which is taken, right? That is what we got it from the manufacturer, and then we need to model them in that process. Find out this equivalent circuit parameters called rate quality factor, uh, A and then RSS and RS. These are the parameters which we need to find it out. The process I am showing you here. Anyway, if someone is really go for the modeling of PV as supercapacitor battery, for them it is required. But our discussion is on this completely united. So I'm not focusing. But although if you wanted to be expert in particular field, you should have a command of each and every component inside your system. So that's why we have done all the thorough detailed analysis both mathematically, theoretically, and then simulation and the right? You can see that. I cannot discuss all the things. There 300 slides on this model. We have limited time, so just I'm showing which are important. So you see that. So this is how once we got a mathematical model, then with this intelligent methods, I use VSO, VFOA method to find out these parameters. Finally, we got it. So these are data we got it. This is estimated parameters using this method. Okay. I will show you the script after the lunch. I will allocate since I have changed some locations from my file. I will show you after the lunch. I will learn these scripts again. Okay, you can see also. Alright, so these are the parameters which we got it, and once we got this, and then we have simulated and we got the IPPV characteristics. You can see that with that script we got what is our RP, sun resistance, panel resistance, and the series resistance, and you see that like our model is given 360.23, and experimentally in the real time we got like 360.24. Right. 360.23974. Oh, so accurate. The tolerance is 0.001. This much small error is there. So with that we have calculated. Alright, then IPV, short circuit current, and the rate current, all the things we have calculated with the help of our ATP. That is battery soon. Alright, so like this we can use our AI techniques to parametric identification, right? Artificial intelligence. That's what we have. Alright, so similarly for supercapacitor potential after that. Yeah, there are more battery, more and model which I have discussed. Okay. So, and with respect to SOC, various parameters which we got for that equivalent circuit of our battery, like no load voltage, and then short term branch, long term branch, capacitance, and then short term branch and long term branch capacitances, and resistance, no resistance, and long term branch and short term branch capacitance and resistances against uh, state of charge are getting varied. Once we have a better parameter, then we can able to find out all the internal stuff. This is what we have done it, and then we find out the process. Alright, so and then we can go for the effect of various parameters on your converter. Right, so now once you know the parameters, then you can find out the effect on the converter, like if you change a small control resistance. Because your resistances are getting changed, you can see that based on SOC, this is a short term resistance, like initially it is high and then go down, something like that. Capacitance also. So how their effect is there on your system that we have investigated, we got these consequences because these are essential to design the converter. Alright, so this is the process. Let me go to the summary and then we'll see how we can develop enhance and then make the system. Alright, so what we need to do is we need to take a new model, take a new planning model. Right, this decimatic and its control system now we are trying to implement. So take a plan model and then we are making once we got a parameters from A, then we can have the equivalent circuits of PV, battery, and supercapacitor, and then we have your converters. Then you can make the system. Right? Once you are having power circuit, this will be the power circuit. Then we need to go for the control. Okay? Different control schemes. Focus with. Yeah. But we'll start with some DC-DC converter because DC-DC converters are integral part of this circuit, which you can see. First we'll build one part and then we'll go to increase the access. Then you can practice the same to make the calculation. I will show you. Right. So you see that this is our system. So what I will do is let me so now let us take this part. We'll do that first with the discovery and then we can apply it in different control schemes and we can make it with this with fuzzy and control. The control part I am applying now. Then we can similarly I have used I told you for parametric estimation of the which is techniques. Right? So you can repeat that process for other so then we can get this. Okay. First we will see that how we can make this. Alright, so if you want to make that model what you need, first you will make first iteration with almost ideal stuff, and then we will go to the more and more accurate models. But I will show you, but we cannot build all the things in one day because it takes time to demonstrate. Right? So I will show you one and you can practice. If you have any doubt or if you are doing, you can always contact. Feel free to. So what you need is take DC voltage source, just get it. And then what you need inductor, inductor means it is like series current branch. And configure like inductor. We need to actually size the values of inductor the first one. That is another side. First that if you want the formulas and look at the values and you can use different for these you already studied some basic power planning courses. So from that you can understand how you can design it. We should take all the things from same line. But I am preferring to take it from specified power system. We should take all the formula from the specified power system. And then see here you will get a lot of errors, but you need to take all the implements and otherwise you will get an error. Try to keep in mind. Like this you can make a DC to DC. Let us take some one converter we have yet. You wanted to control its voltage or current, you need to sense them. Let us say you want to check the inductor current or the flag, take a measurement. Alright, so then continuing in the reference parity constant, and then you need subtractor, and you can take a sum and you can change the sign, it will become subtractor. This is my reference, this is my actual. Then we need a control. zero income. It needs two inputs. One error and second one is change. This will be changing error. We need to take a box, marks, and process two things. This is the error. This is the change error. We counter voltage and then we need to take a modulator. Now, everyone will take. So like this you can make, and you need to take this will give you the pulses that this is like simple procedure. One can write with the if you need to take its own proper values, then things will be. I will let me show you. So we are going to this kind of proposing this number functions, and then we need to take it this folders, right? And then we need to store this. And so this is what I saw. And but here I kept the specific values of our case, like hungry, and then 200 microcard, and 7 more resistance, and then 20 volts, to 30 volts. So that's what I take one by 30. And these are the way I have shown in earlier. That is how you can. Okay, so now, okay, so you can see that. You need to create a rules, like what happens, you need to define the number sequence, right? So error, like see that negative big negative small 0 and positive small and positive big. Then number sequence for change in number, then negative big negative small 0 positive small and positive big. These are the number sequence for changing and here are number sequence for my utilization. So into big and into small, into zero and positive small. Right. So like this you can create a number sequences. Once if you want you can also change that you can add number sequences. You can do that. Okay. Once you have created a number sequence, then you need to create a rules. Like if average negative change average negative, what is your positive? Like that, like it, like depending upon the disease, you can also understand it. And once you are having a mathematical model, then you can from the mathematical model, you take a reference and you can work and you can change the positive side and negative side of the positive. Means we are finding out delta t. Means the utility side changing the delta. That is what I am finding out. Engineering means positive because small that change in increase is positive small. Okay. If it is small decrease in the delta means change in duty ratio, then negative small. Like that, we have defined the membership concept from integration, and accordingly I have written my once we are having that. Okay. So I have kept it in the workspace, and from the workspace I am calling here. So you can see that. Then, you can see surface. These are the surface from even x-axis is ever and the axis are also being out. Okay. So that is what I have done here. So this is like output is not duty ratio. That you should keep in mind. What I have done, I have done change in output. I have taken an initial duty ratio and that I am just changing my duty ratio. Okay. Delta I am calculating equal delta D. That is actual cycle will be applied to my model. That will be the case. This is what I have done. That is what I have done. Alright, so now you can run it. It will be so it takes time, of course, because if you increase the models, it will take more and more time. Depending upon our numbers, that is done. It is like here you can see the status that it completed 2%. Well, let it. So, these are my work. So, yeah, it is. Like this, you can see it within my desired as prescribed. So like that, you can make one control, continuous control to the matter. Now, if you have done one time, then you can check the stability. I think I am at this point. You can see that it's template is not like this. You can make one and with control and apply to go back. We'll stop here on this topic and we'll continue on to the values because now one to one is the time for the discussion of article. So we'll discuss on the article and then we'll continue. Then we'll go to the DMS and all. Let me on this. And you can see that how we can make this model also. Now we got one part. We can say that this part we got it. We have completed this part with that basic control. Like that you can apply other parts. That we will see in the article. Now we'll discuss the paper, kernel paper discussion and we will continue now discussion of paper. Now article discussion.
Oh, yes, sir. You continue. Yes.
Article discussion.
Oh, yes, sir.
So we continue this simulation stuff up to now. Now we start here and we will continue our article. Let this time and so that is perfectly aligned. That is done. Then go to our article description here. This state of our technical format over these and HESs. These are content. There is actually two parts of the this. Let me open another part also. There is a part. There is a two parts. We'll discuss that. So let me continue discussing. Yes, we will discuss. So first one we will discuss now is one. Unless most of the stuff we have discussed and in this we will discuss. The first part we will this fabric produces with various components because it reduces review between me and Nigel Key and then Andy Warkal and then Russian colleagues. We have worked on this paper. Then another discussion. Okay. So this paper actually we have done a thorough review on various architectures of DC microgrid, and also architectures and then converters and then control. But, mm, related to DC microgrid, DC microgrid setup of it. So you can see that here, what is the complete system? We have solar and then battery and solar. Then we have DC. Here we have, as I said, that our key area is that we need to have monitor the load and monitor the PV power. Anyway, if you want to maximum load, you need to send VPN and IP. Accordingly, you need to control the DCDC converter, which is attached to this PV. That will be controlled through some kind of MPPT. There are various MPPT techniques out there, like farming and DMO, or internal connectors, constant voltage, also it's a fractional voltage, fractional voltage that we also fractional short circuit current. And we have neural based MPPT, a fuzzy logic control. There are various MPPTs that we can apply. Here, this blue color boxes, like I mentioned, they are measurement. Right. Coordination is very important in case of DC. Further, there are various control architectures like distributed control, centralized control, there are different control, decentralized control. Various that is another on the side of the discussion. But anyway, now discuss. Here, what we want is we need to have a data at various points. Right? So that is what I mentioned. That way, the data we need to get, and then we need to calculate various parameters. Like one thing on the voltage and current, another thing on the power. And as a complete power which we need to get it from the energy. As a there that we are giving a load prediction is there as an input, and then we have this difference between DP and load as an input. This energy management. There we have the two subsystems are there. One is the SOC management, state of charge management. Accordingly, based upon the state of charge, we need to allocate the power from the battery. There is an algorithm there we need to develop. And once we have done that, then we have this voltage and current. Right. So this is like what you say. There is a different hierarchy, like we have different layers of a control. Right. We say that it is a hierarchical. Hierarchical. If you want to see that state of different architectures of control, like hierarchical control. Anyway, we have let us discuss. Similarly, we use these yeah, we can talk about this. Because it is not in our plan of this. But I wanted to show you that I wanted you to make aware that various areas where you can focus depends upon our research area. That's why I wanted to right? So, I did not so here, once you are having this first layer where you are talking about especially another layer is the power allocation. Once you know the power is allocated, you have a battery voltage and then that will decide our current preferences on the batteries. That will control this battery. And that is what you are like from this project. You can see that we are feeding the data of the superconductors. This is another actually. Right? And various type of VSS technologies are there. What we have here. Anyway, in the afternoon we have a related session related to this BMS capabilities, small ones, battery technology, and BMS equipments. Right? That we get it in this para and applications of this and then we know that in some cases we need a direction control, DC machinery, some cases solar power converter must be implemented. It's not there are some variants of the capacity based. We need a lot of what kind of DCs we need to use. Yeah. And then architectures of Kannada topologies. Right. So here there are various type of architectures which we have discussed in the morning a bit. Then there is a different power sharing methods are there. Like this is like where we are using this A and M. That's what I said at the beginning. That we have here. And then various power converter topologies which are generally used here. Right. As I said that in DC microgrid cases we are using this A and M for power sharing. And also for the control is here some like fuzzy. Right. So in these cases we are utilizing this control point of view of this. And the parameter guarantee identification also we can use this to you see that there are a lot of various methods like architectures, what are they which we have discussed, passive, semi-active, and active, more than two. And we have power setting methods like low pass filter based, and wavelet filter based, adaptive fuzzy based, and general FLC, and we have roof control, and then we have EEC, we have decentralized. And these are all things I have included in the you can see that there are a lot of regular where we have and summarized there in this here. They like they review on this both PMS as well as power allocation. From these only I kept it only. These are not emerging power management, adaptive energy management, and active control hybrid, stochastic energy source assessment. anyway, this Sunday I just organic guidelines and control method, management, low and high frequency power enhancement, the various research purpose we have captured it and someday they recommend research review like here what kind of there we have simulated most of these things. Some of them is continue, time, these are the process like I said, like non-computers, voltage, direct bookkeeping estimation, adaptive systems, hybrid methods, like that primary control, secondary control, and then hierarchy control, tertiary control. These all together is centralized control, decentralized control, group control, and easy one is extended group control. Right? So decentralized control. And the power sharing was virtual impedance. By control virtual impedance, we can change the power sharing between the sources, backup power sources. Maximize is extensively current run, right? And this is adaptability of anyway, like that, there is various methods. As a summary, I kept it there. So these are the various methods of the which are there. And, different control schemes, so different work monitors. A basic unit work for boost, work and boost, cards, data. Can use it like analyzing unidirectional work for which cascaded with specific purpose. There comes under category of which program topology. And another classification like source switching. Fully source switch work and easy. And there is a multi-phase converter like MJ, MBTC with the tertiary couple multi-level topologies are there like bank approach based cascade multi-level and multi-level is there like that. And then we have like similarly, these are the right hand side is like isolated, non-isolated, and the left hand side is like isolated. Isolated, we have connections not like that. Right, like that we have and which side we have legal activities, single activities, and yes, we can like multi-port, soft switching is the LLC, right? Objects, LLC, SPC, boost, boost companies, boost societies, tolerance, like that, there is a various management, for management, national transformation. Similarly, we have also reviewed various control techniques AITs, various switching strategies are applied for this. We have single phase teaching strategies so that is all I can here in the summary of the previous lecture. Alright, so these are lectures which we have discussed in the PPT. These are how we can these are the summary from the previous discussions slides and so on. I have it here because we cannot keep in the background of the and then moving upon the alright, so the power allocation strategies. This is like calculator based. So on the linear non-current we are using only rod is P power level for lithium and power level for once based upon our design, we have this comparison on the architectures. Which one is right? Right. We have passive, active, so which we are shown that here. And then what are the primary sequences that we can use here? And how many binary species are here? The next row, like in passive 0, batteries and get 1, fully active is 2, and there are levels, maybe 3 or 4, something like that. Converters, volumetric efficiency of passive and battery semi-active. Software performance will be defined because we have number of capacitors and fully active will be similarly as I said that's so we can get efficient software capacitor utilizes very good in case of software capacitor is semi-active or fully active and multi-level. Where you are utilizing fully the software capacitor. Cost is very low because you don't have any kind of conditional converters in passive cases. That's what we have. Yeah. Other cases, highest is like multi-level and fully active is like higher. Semi-active cases. Voltage operating current is very low in case of these as I said earlier, and battery is semi-active. Fully active is moderate and multi-level. Power losses are low in case of passive because we don't have any and it will increase as the convenience of reliability is more if you have less components, that is possible in case of passive. That's what we have. Battery discharging time, it will take more in case of reactive, it will be less in case of passive. Battery life cycles are highest in case of when you are having elegant disease. So, multi-level is highest. And design complexity is highest in case of multi-level. Passive, there is no any design complexities. That's what we have. And what are the future directions? Reduce component from computer, reduce component from application. And then input address from module names, and then soft switching converters. So a lot of converters power switch based, and then moving towards the soft switching efficiency, like FPS, LCS. So and another direction is that modular features people are working on that, so modular architecture so that you can easily plug and play with additional when the rating of the systems are getting increased. And how some people are working on that, and some people are working on control aspects of the DC microgrids and architectures. right? So like different because controllers plus a micro, including some parameters like that, second stability, all these things, right? So for example, adaptive, or then what ESO, ESO game, different million controls of digital control, real time control system, and digital platform control, adaptive. So like this, and if you consider that here, there we are discussing on architectures, now we are discussing on power controllers. Right? So non-aspect number boost. So you see that it is a bidirectional number boost, all the switches are bidirectional. So if one side is like buck and other side is like a boost. This is like non-aspect buck boost derivatives. Now it is like buck boost. If you remember that it is like a buck boost. We have here positive and here negative. Like we know that the polarity will change in case of buck boost. There are biases. Buck and boost case it is like both are positive. Input is positive, output. But polar conversion is there in case of buck boost derivatives. Similarly, like on a curve derived ADC, that's what right after somebody would have known that the ADC or non better. All the switches or the power management we replace with the bidirectional. This will continue in a bidirectional. Like curve derived bidirectional. And then zeta and sepik derived. These are both the operations like zeta and sepik. This is sepik, this is cascaded bidirectional. So we see that two VDCs are connected cascaded. This is earlier on VDC. Switching capacitor by bidirectional, like switching capacitors. Yeah, this capacitor getting switched with this switches so that you can switch capacitor. And then fully stop switching. See that because resonant components, we can make use of this resonance of these resonant components to switch the switches using resonance concept of the classes. And then multiphase concept like enclave things like using bias. Any above one then current setting will be increased and then power handling capability will increase and switch that switching although the switching peoples will be decreased on the input side current. This is another negative. And four phase or four grids, I believe where this is just supplementary. So two winding two winding like four phases of grids. Right? So there is a multi-current concept flying across the place. Here I want to alright, so we have this multi-level like FC based for level. Multi-level cascade. We have cascade. Multi-level cascade. And like bi-level and multi-level for multi-level. Bi-level, multi-level, modular capacity. This is the capacity. This is. So, as long so far we have discussed non-isolated, bidirectional flyback. Like in flyback, there is a diagram there, now we are representing the bidirectional. Push-pull also we are doing the same. Then we are discussing forward bidirectional method, and then accelerated data. This is accelerated data. That kind of subject. And then single active measure is only one side is active, and one side not active. Single active is both sides we have activities. And then DL operate is like operates, primary side is the second job. Is a dual operates. If it dual activates, full page is active. Now it is like operates on this side of the orbit and full page. One side is orbit and another side is the orbit. Multi-port. There are multiple ports are there. This is my hand side and this is your side. And this is one port, this is another port. This is a multi-port. Like it is interacting with that on the side and on the other side there is an activity. So this is a multi-port gap. Then full page series is like full page layers. This is our speed. This is set operating environments. Low and more problems right, so LLC, like LLC. This LM of this transformer, this LM, this LLC. And SPC is a series parallel current. Series parallel. Something SPC. Right, so, and then like boost programs. Like they are in boost mention as well as full bridge mention. So that's why they give me full bridge, boost full bridge, and not for whereas this select is the when these switches are these two switches charge. These two will feed the power together and as one as that's why we get a boost capabilities. That's why they get a boost and then full bridge. Also, you can say boost we like to do both the boost operates. One side is the operate and another side is the operates. Right, so this is like two isolated, two stage isolated. This is a one stage, this is another stage. This is isolated, this is two stage isolated. And this one is next one is triangular current mode. So you have a current. Another one is multi phase properties. Like multiple, we see that when we transform. So three phase current. Current is like this is the current. We are there are three phases. Three level. This is one of the analysis. Like three level frequency on this is three level frequency. This is like LLC. LLC. Three level LLC. Right. So that's what we have. Three level. This is not next one is frequency level. This is like frequency level, and by controlling them, we are getting three levels. The output. Upper we have to do several level. Now there is isolation. Which one is better? Whenever you need resolution, you input an output, or we need to go for isolation of topology, if there is a need, you can go for the non-insulated. If you want a very good very range of input voltage variations are there, then you can need to go for isolated. Otherwise, you go for the non-isolated. Isolated knowledge are also various types of degrees are there, depending upon what requirement you need to select. Right? So that we can discuss when to what you have to select. And sometimes having universal, sometimes variation. So in case of solar, you need to take unidirectional. In case of battery, which cannot be selected, which cannot be selected here, you need to select the proper. And some topologies are like voltage, but some topologies are current. Current is a some topologies, even we have impedance that cannot go to the right. So based upon your available sources and load requirements, you need to select because you want to get a step up in a single stage manner, then you need to go for current where you want back, voltage back. If you want both, then it is a bidirectional, like there is also. Right, so and then some classifications are hard switches, soft switching, will give you the distancing, but you need to have more component, right? But hard switching having a problem, doesn't need any additional component. It is already converted from high MCR, EM, right? So those are by which topologies are concerned, which can be activated. You can see them like what each component is concerned, which category I have. Alright, so alright, so and then component size weight value, then for each topologies, whatever I have mentioned, I have summarized in a table. You can see that full comparisons are there. Which topology is taken from which reference and which figure, what is the gain, what is the vector, capacitance, right? So I kept it here. Everything is transformer, right? This transformer there, transformers are there, winding are there. I kept it there. So this is the characteristics and which type of current element that I kept it here in a comparative manner. So, and then you see that the application is termination and then what is the nature of the current. Implied by you will get a discontinuous input current. The continuous input and output you will get the push-pull, for like that I get it each or like that you can see that comparative analysis gain and then what is the current non capacitors and the input current nature and then sort of applications and calculate what we are. Alright, so like that we all the review topologies against failure numbers and the references from the solution we have taken that. Next one is wide where which topologies are good in case of wide voltage range. The topology is shown in figure 138 with high frequency components like transformers. They will get a high, good, wide voltage variation. So you get it, so that we go in solar power because of transfers and radiations is very you want to affect from the morning to evening. So radiation is changing from 200 to 1000 by 5 times variations are there. Maybe to 100 to 6 times variations So your voltage is currents are varying. So in that case, if your wind is also there in your visual then wind speed also varies. Then the voltage and current may vary. In that case, you may need a wide range of voltage converters and then you need to go for figures carbonation that. And rather than cooling requirements, like some component they are using hot switching and some topologies. There are not of there are soft switching typically low losses. And low losses, cooling requirements will be low and hot switches will have to go for good cooling requirements. Maybe with the force cooling, in case of force cooling, we may need to use some kind of heat sinks external finance, or you can use liquid cooling also if it is going for a very high power items like that. Like that, summary we have kept it on the review architectures and that. Now there is some discussions we kept it like feature directions and things like that. Like as I said that like topologies with reduced component count is always a decent uh, direction where people can work. And then increasing input operational voltage range, if you are having a very high gain converter, they will be always a better. So because they can be adaptive in nature for people like voltage variation. So that so that you can do it. And then soft switching converter like this is converters with high switching frequencies and low switching losses or low convection losses are always a good choice. And it can be a good permanent solution for DC. Modular structures of converters is highly essential because you can plug and play based upon the power requirements. You can switch the some converters on, some converters are off, based upon the power requirements. So you can keep some converter modular. In modular way, some converters are on, some converters are off, based upon the load requirements. So that those converters will be kind of a losses. Right? So like the overall essence may increase. That means we need a modular structure, good control concept we need to employ because our converters are highly nonlinear when we are making converters with the decimal circuit overall system is highly nonlinear. So we need, and also there are a lot of variations there in the system like line, load, and solar radiation and speed. Whatever like parameters they may vary, but your controller once you have designed, the parameters are fixed like APK, if it is maybe a fuzzy and your rule basis and your consequences are fixed. Your system should be so robust and they should be so adaptive to sustain these variations in the system. So that you need to take care while you are designing this. Alright. So like that you can go through these papers. So like these are references of the category. Yeah. So these two papers have a detailed discussions on the various architectures and then problem after topologies applied for this solar power distributed. Okay, so uh, okay, so like that we have various various this is with different control schemes and similarly different converters we have done in human example is compare these two. This is V1 and C1 also. And these three simulations done. Anyway, we'll discuss these things in the afternoon. This afternoon we will also like more into batteries of this grade. Right now we can enhance the performance. We'll discuss and even after one. So we'll start our discussion here like the simulation designs, and then we continue our discussion on the home. Right, so we'll start here now and we'll start. Thank you.
Dear participants, take the lunch till meet 2 o'clock.
ఏమన్నా సాల్ట్
నేను కొంచెం అబ్బాయికి చేశాను. అది వేరే గురించి ఈవినింగ్ నాకు చేయమన్నా అబ్బాయి.
అవసరం పిలుద్దాం So, good afternoon, participants. We will start the today's session 2 afternoon. Please listen actively. Thank you.
So, good afternoon. Friends. So, let us continue our discussion where we are starting in the morning, and then we will go for our discussion on battery management systems for grid connected systems as well. So, yeah, so before going for the lunch, we have seen how we can make a DC microgrid, right? So, and we have applied this physiological to control this power converter, like we have designed it for like battery based DC converter. Similarly, you can extend the similar kind of analysis to the supercapacitor, and then you can use it to like otherwise you can use mixed nature of controllers like some are fuzzy, some are PLL, some are GPM. And so even in the bias also we can play and various simulations with this intelligent controllers for various applications. So we see that one at a time. So first we'll discuss something on our afternoon topic, and then we'll discuss about this and some other applications of fuzzy logic. Right? So if you see that get augmented right? So this energy storage element plays a vital role. Right, we see that like the structure of a vehicle, we have a batteries and then automatons. These batteries are employed with some kind of a BMS. BMS plays a vital role. What is BMS? We'll see them in the coming slide. Why we have to do that and how we can do the simulations of this BMS. Alright, and then like proper there will be motor and then mechanical transmission and differential system will be there, right? And this arrangement will be there in case of electric vehicle. So overall, the source in case of AV typically is like lithium ion. What are the other battery technologies we have? We just have a quick review, and then we'll see that this BMS somewhat in detail as now discussed in modern games. So the same thing you can use it, similar kind of management systems you can use it for supercapacitors servers, supercapacitors for needs. Alright, so some organizations like in India we have this case where they are developing indigenous batteries and they are developing indigenous supercapacitors. There is a need for them to develop these battery management or supercapacitor management system. If someone have expertise in that, so you can develop it and you can discuss with them as per their requirements. You can customize it. None of our discussion with the research CP, this is CRC especially level actively. Anyway, so we'll see that like volume of research publications in this battery technology. You see that it is like in 2006 it was quite low, and then if you see with respect to year, it is quite progressive in nature. You see that number of publications are crossing more than 5,000. And like it is exponential in the means that is huge need. If you are doing some kind of research, we know that research necessity is a matter of invention, right? So you should have some kind of necessity, then only you need to do research to fulfill the necessities. Alright, so from this, why I kept this slide is that you can understand that there is a huge demand is there in case of this battery research and BMS technologies, right? Oh, and you see that in the left hand side. These publications made by most of the country-wise specified. You see that in China they are doing a huge research, like 36% of the publications are coming from China. Chinese software developing a lot, developing a lot on this field. 18% is coming from US and Europe, 14% plus Korea, 10%, Japan, 7%, like others likely comes into that others like all together 14%. So countries like in India, we are a big customer base. So since we have a big customer base, but if we can develop here the technologies, then there is a huge benefit to the customers as well as the designers and developers. So it is better if someone can work on this kind of area and then you can develop some kind of technologies to batteries or battery related areas like BMS and something like that, so that you will have a huge market that you can understand. Need is and then you see that like manufacturers now, so earlier we have seen where the people are doing research from the like publication point of view we have discussed. Now we are seeing the manufacturers. You see that most of the battery manufacturers like lithium ion manufacturers are from Korea, South Korea. See that a lot of companies are there, they make these batteries. Right. So like 40% of the batteries are coming into the market from this South Korea and then Japan, China, US is like 1%, and then others are like 6%. Right, so this lithium ion right now is somewhat costly. We are using it in case of electric vehicles, in case of lithium we are use lead acid and that, the cost effective solutions. We will see the problem what are the technologies are there in case of we see that like if you see charging and discharging phenomena in case of lithium ion, difficulty is there in some kind of cathode, anode, in between, right? So, and charging and discharging, like electrons are moving from cathode and side, discharging. You see their characteristics, similar characteristics of lithium battery charging, left hand side is charging and right hand side is discharging. So in right hand and left hand side in figure A, time axis is x axis is the time in hours and left hand that in the same figure y there is two y axis like left hand side y axis voltage and they can generate current. You see that based upon, and we have three graphs out there. One is on the right hand side, there is a two y-axis, one is the charging capacity, second one is the current. Right? So you see that from these are different characteristics of the battery while charging, right? So if you understand this, then only you can make a good charger. We'll discuss on the charger also, like one EMS and chargers are integrated part of this RN microchips. So we should understand their physics in detail. If you can understand the physics in better way, then you can able to design EMS chargers. Right? You see that from this figure, you can understand that initially the current you see that is like constant. When current is constant, like with some magnitude, and then voltage is rising because we are charging it. We can also notice that state of charge is increasing. And once it is reached to certain voltage, now we need to decrease the current. Right? Current is being decreased. Current is being decreased. We are not decreasing. So current is being decreased. If you are charging, right? State of charge increasing, and then once it is reached to more than 90, then the slope of this SOC is changing. Right? Earlier slope is something different, and once it is reaching 80%, the slope is different, and then the current is very not. Very right? And voltage is like almost constant. You see that once it is come to state of charge, once it is reaching almost like 70% somewhere, 80 you can say there the voltage is now constant. So from these characteristics, why we are discussing the characteristics, you can understand that we have to design a charger to charge this with two modes. One is the constant current mode and second one is the constant voltage mode. So initially you see the current is constant, after that voltage is constant. So you need to design a charger like this to meet this demand, otherwise it's a huge problem to your battery. So we have to, from this graph we can understand that it is operating into one is the constant current and then constant voltage. So we need to design a charger effectively which can operate in CC and CC. Okay, we see that in figure B, we can see that with respect to discharge capacity, how the voltage profile. See that with respect to this discharge capacity, right? As you see, at initially there is a if initially the voltage EMF is high, and then the voltage is high, and then after certain percentage of SOC, the voltage is now constant. Once it is like now discharge capacity is very high, then what happens? There is a huge steep curve of the voltage. Voltage is suddenly decreasing. Initially, voltage is decreasing from some value like 4.3 to 4, and then it's constant at 4, and then after 5.5 discharge capacity, whatever, then it is going down rapidly. Right. So current is increasing. You can see that. Right. So we need to means there actually the internal resistance keeps changing. So we need to operate always. That's why the manufacturer they suggest you to either don't discharge too much of your battery or don't charge more. If both the case there is a problem. You have to operate always between 20 to 80%. If only 80% there is a problem. 80 or 90 depending upon the battery. Overcharging, over discharging also. So we can understand this from this character. We can understand what happens in that there. In this region, like 20 to 80% is like the numbers is almost constant, but below and above there is a problem. More resistance, more masses, and more heating. Losses will not sit ideal in the system. It will create all those losses, get a heat. So in lithium based batteries, there is a lot of variants are there, like lithium cobalt. You can see that all these technologies are reviewed and then kept it on axes like cost, lifespan, and performance, safety, power density, energy density, specific pro specific energy. Out of 5, it is rated and it is given like in cost, it's like 3 out of 5 with respect to other battery technologies. Right, lifespan is 2 out of 5, and performance is like 3 out of 5, something like that. You can understand. And then last, we can have once we see all the technologies, which you want a car which is having a good the index value. Like that. So this is like lithium manganese, lithium cobalt, lithium manganese, right? So these are like lithium manganese, like in terms of same parameters being compared present here. And the next one is lithium phosphate. We have LiFeU, and then MnCl, and then NCA, nickel, cobalt, lithium, and lithium titanate. So we have different batteries of lithium, then we can see them for the same parameters we have presented. So based upon your requirement, you take. Alright. So in some cases you want very good car like lifespan, some cases you want good performance, some cases good safety, power density, or energy density, specific power, specific energy, or cost, economically viable or not. Based upon that, you need to see what all parameters you want, summarize them by total, how many marks it is getting, accordingly you take it. And then you see that in case of lithium ion based battery based vehicle sales, it shows the demand of this battery technologies. You should understand demand, and then you see the problems of the existing things, and then you try to solve that. Alright. So you see that here there are 3 different types of EV, PHEV, HEV. Every electric vehicle, plug-in hybrid electric vehicle, and electric vehicle. In other cases, we are using lithium ion batteries. See that their sales is like increasing like anything. HEV is like almost constant from 2017 to 20, but you see that PHEVs and EVs, their growth is increasing a lot. Right, so it shows that there is a huge need for better battery technologies along with associated components of the battery like BMS or chargers. Right. Now here is you can see that there are various technologies around the batteries, not only lithium ion, like lead acid, nickel cadmium, nickel metal hydride, zinc chromium, metal chromate, and the lithium ion. You can see that there is different technologies are there. Like their values have been compared, so you can understand that. In case of energy density, we have like 30 to 50 in case of lead acid, whereas in case of lithium ion, you see that it's like 110 to 160. This is what we want. What does it mean? It will give you the more energy in a less weight. That is the energy density. So this is what exactly we want. We wanted to have a very good less weight systems. Power density, you can see lead acid is 180, whereas the lithium ion is 1800, 10 times more. That is a huge benefit with lithium ion. And the normal operating mode is 2, whereas here it is 3.6. Operating temperature is like minus 62, minus 20 to 60, it is almost here in lithium ion. Like cycle life, it is like 200 to 300, whereas here it is 500. So you are getting good cycle life. Right? And charge efficiency is 100%, here it is like capacity 79. Energy efficiency, voltage efficiency, you can see that overcharge tolerance high, very low. Actually, you cannot in case of lithium ion, you cannot overcharge, which is a problem. So that is what your BMS you need to take care. Overcharge tolerance is very low. That's why there is a problem that if you overcharge these things, no, it is greater. And self-recharging is low and very low in case of the lithium ion. Intercooler systems. So they are not like discharge even you are not much. Thermally stable, they are most stable in case of lithium ion. So that is what a good thing we are having in case of lithium ion good things with respect to their competitive technologies. Now here you see that you can understand that there are different technologies which we have discussed. Right. So see at a cell level, you see that in case of lead acid it is around 2, but whereas in lithium ion it is around 4. Right. So the uh, best thing which we are having in case of lithium ion. So the cell level voltage is also very high, so you can design easily for higher voltage rating battery packs. Right. So, whereas like in case of zinc, manganese oxide, case is very low. Nickel, nickel, cadmium, and nickel metal hydride also is very low. You can witness on this side. People research consider how much low you can see with the map. Alright, so here we are comparing this volumetric energy density, geometric and volumetric. Right, so you see that lead acid is very low, lithium ion is very good, lithium metal is somewhat unsafe, so that's why we are ignoring that. Lithium ion is very good compared to nickel metal hydride and cadmium. Witness from here. Right. Uh, and operating voltage profiles, you see that operating voltage is like for different cases, right? Different actually combinations like of lithium and other metals, right? With that we are having different types of lithium technologies for the batteries they have adapted, and the comparisons I kept it here. You see that they are given from different references I have mentioned here. So what I wanted to say is that among all these things, we have this lithium ion and lithium FePO4, right? This LiFePO4, they are given a very good market in this EV. You see that. So these lithium